Okay, welcome back. And today we're going to start chapter 7. And chapter 7 is one of my favorite chapters because it's about sets and probability. So we're going to talk about sets. What is a set? It's a very straightforward section of chapter 7. And we're going to talk about how different ways of describing sets and dealing with sets and the notations and therefore, because that's going to be one of the building blocks of probability that we're going to use. So 7.1 is all about what sets are. So these are just sets of objects. Could be anything, right? So we can write an element belonging to a particular set. So a set is a collection of objects. And you can define the objects as whatever you want. Jelly beans, numbers, shoes, candy, whatever the case may be. Okay, so we can write an element that belongs to a set in what we call set notation. And so the curly braces denote a set. So we say the set of all x, and the vertical line means such that, and then the rule. After the vertical bar is the rule that says, hey, whether you can be in the set or not. So if you satisfy the rule, you're in the set. If you don't satisfy the rule, you're not in the set. So this would be set of all x, all objects x, in other words, such that what? X is a state whose name begins with the letter O. So if the state begins with the letter O, it is going to be included in this set. If it doesn't begin with the letter O, then it won't be included in this set. And so the solution for this is going to be the states that belong in this set, which is going to be the set of Ohio, Oklahoma, and Oregon. So notice that we've got the curly braces here because remember, curly braces denote a set. So if we're looking at a set of objects, you have to have these curly braces. Okay, I'm a stickler about that. So you wouldn't just write Ohio, Oklahoma, and Oregon. That would just be a list. Okay, to denote a set, you would have to have the curly braces around it. Okay, very important. So now what is a subset? Okay, so you have a set of objects. A subset is any set where the objects in one set, the elements of one set, are also in the other set. Okay, so if we have two sets A and B, we say that set A is a subset of B if and only if A, by the way, this is the symbolism, so we use this as subset or contained in, right? So A is contained in B. A is a subset of B, okay, if every element that's found in A is also found in B. Okay, so if every element of A is also an element of B. Now, a proper subset is a little bit stronger, okay, which means this symbol, okay, this means proper subset. So, which means we're not including the equal sign, the underscore, the equal. You could look at this like an equal. So that means we're not going to include this the case where A and B are the same. Okay, where all of the elements of A are in the set of B. Okay, so a subset does include that. Includes the possibility that A and B are the same set. Okay, a proper subset does not include that. Okay, so again, proper subset is where A is not equal to B. Okay, so make sure you understand that. Okay, so now here, it says decide if the statement is true or false. Okay, so in this case here, we've got this set and we've got this set. So is this set a subset of this set? Okay, so let's use the definition. This set will be a subset of this set if every element in this set is also an element in this set. So is that true? And the answer is yes. 2 is in both sets. 4 is in both sets. 6 is in both sets. So therefore, this is a subset of this. So the order of the elements don't matter. What matters is if they're inside the set or not. Okay. So now here's a couple of properties that you're going to need to know. Okay. So one of the things we're going to look at is what we call the empty set. The empty set, which is denoted with this circle with a slash through it, means it's the set that has nothing in it. The set that has no elements. Now, because we cannot find any elements in the empty set, because it's empty, that are not in A, then this would be, well, trivially true. So what we say is that the empty set is a subset of all sets, any set. Okay, so this will always be true. Also, a set is a subset of itself. That will also always be true. A is a subset of A. Okay. Now, is A proper subset of A? No. Okay, but that's not what we're saying. We're saying A is a subset of A. Okay. So this is always true. Okay, so this is another trivial. This is trivially true, and this is also trivially true. So these are two properties that are always true for all sets. Now, one way to figure out, hey, how many subsets are there? How many possible subsets are there? Well, there's a very easy way to figure it out using what's called a tree diagram. Okay, now, the tree diagram allows us to be able to count how many different outcomes we could have, how many different sets that we can have. So, and here's the thing, right? If we have this set, 7 and 8, we find the subsets of 7 and 8. So we look at each entry, right? So here's 7 and here's 8. So either 7 is going to be in or out. Those are only two options. And then 8 is either going to be in or out, right? So in the first case, 7 is either yes or no. Is it in or is it out? Okay. And then once it's in, right, if it's in, then we decide that is 8 in or out. And for both of these. So these are all cases. So there are looks like 4 cases. Okay. So that means that if we go down this branch of the tree, we've got no and no. So that's one option. So we could have the empty set. We could go down this branch and this branch, which means we have the set that includes just 8. And if we go down this branch, we've got the set that includes just 7. And if we go down this branch, we've got the set that includes all of them. So notice that we've got the case that we have everything, and the case that we have nothing, and then everything in between. So we end up with 4 possible subsets. Okay? And now we can expand this to 3. Let's take the letters A, B, and C, and let's see how many different subsets we can get using our tree diagram. Well, again, for A, we could have yes or no. And then for each branch that we go down, for B, the next one, B, could be yes or no. So it could be yes or no for this one, yes or no for this one. And then if we go to the third one, it's going to be yes or no for all of the 4 branches. And so what do we end up with? We end up with 8 possible subsets. How do we get each subset? By going down each branch. We get no, 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 no. Excuse me, no, 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 which would be the empty set. We can go no, no, yes, which would just include C. We could go no, yes, no, which would just include B. Okay. We could go no, yes, yes, which would include B and C. So as you go down each branch, you'll get all 8 subsets. So good way of listing the possible subsets. Now, the restriction, not the restriction, but the problem with tree diagrams is they tend to get messy. So if I was to expand this to a set of 4 objects or 5 objects, your tree diagram can get pretty messy. Okay. Luckily, there is a formula that will tell us how many distinct subsets there are. So if we have a set of k distinct elements in a subset, then the number of subsets is going to be 2 to the k power. And the reason why that is it uses actually the fundamental counting principle that says, hey, if I have k categories, okay, and I can only choose one object from each of the k categories, then all I have to do is use the counting principle and say, I'm going to multiply those numbers together. So how many different outcomes can I get? Okay, well, in each of the cases, in each one of the elements, either the element's going to be in or the element's going to be out. So for each element, there's two options, right? Either in or out. Well, if you take if there's 5 elements, right, and you go down and each one has two options, in or out, in or out, in or out, in or out, and then finally in or out, well, what do you do? You have 2, 2, 2, 2, and 2. And so the fundamental counting principle says we're just going to multiply those numbers together. And that's where we get 2 to the k, because for subsets, it's always going to be the same. It's going to be 2 to the k power, where k represents the number of distinct elements in the set. And the key word is distinct elements. Okay? They can't have, we're not going to count repeats. Okay, so now if we look at this and we say find the number of subsets for the set, again the set X, such that X is a season of the year. So how many seasons of the year are there? There are 4 distinct seasons. Okay, fall, winter, spring, and summer. Okay, so that means if we take our formula 2 to the k, where k is equal to 4, we get what? Well, we get 16. So there are 16 different subsets ranging from all 4, okay, to all, to none of them, right? Okay, also notice that if you haven't noticed the pattern, it's like every time we add an element, the number of subsets doubles, okay? So when we have one element, okay, we only have 2. Okay, we either just have 1 or we have none. Okay, when we increased it to 2, we end up with 4 possible subsets. When we increased it to 3, it doubled to 8. And when now we increased it to 4, it doubled to 16. And if we double, that's, again, we're taking 2 to the k, right? Okay, so there's the answer. Okay, now, how do we represent subsets? So this is what we call a Venn diagram. Okay, we can, or an Euler diagram. Okay, so Venn diagrams are a good way of representing sets of objects. U is the universe. That's the set of all objects that are under consideration. Okay, so again, that the universe will be defined. And then in there we have 2 sets. We have set A and we have set B. And notice that set A is inside set B. Okay, so in this case here, we would say that A is a subset of B because A is contained. Get it? Contained. So A is contained inside B. Okay. Now this also includes, because it's a subset, not a proper subset. It would also include the case that A and B are equal to each other. Okay, but for the time being, for a subset, we usually write one circle inside or contained inside another circle. So now here's another thing we have to understand: the complement of a set. Okay, now the complement of the set is everything that's not in the given set. Okay, so if I have a set A and I would like to describe the complement of A, well, the way I would describe the complement of A is everything that is not in A, okay, but in the universe, right, in our universal set, okay? So in this case here, here's the set of A. A is everything that's inside, all the elements that are inside A. The complement of A is everything that's outside the circle. So the shaded region here in pink is A complement. We use the prime, so A prime is A complement. Okay, so the definition of A complement, or the complement of A, is the set of all x such that X is not an element. So this symbol here is an element, which means you're an element of the set. Okay, so in this case here, the complement of A are all elements X, such that X is not an element of A, but is an element in the universe. Okay, that's the way we define the complement of A. And this Venn diagram is the way we visualize it. Okay, now the intersection of two sets. Okay, so in this Venn diagram, we have two overlapping circles. And so the intersection is where the two circles overlap, where they intersect. So intersection is where we use the upside down U. So A intersect B. And this, again, set notation, the definition means the set of all X, such that X is an element of A, and, keyword, and X is an element of B. Okay, so we depict it as this. So here's our universe, the rectangle, and then inside the universe we have two overlapping circles. And so the intersection of A and B are all the elements that are in both set A and in the set B. So in this case here, let's answer some questions. So we define set A, notice the squiggly braces. We define A as a set of 3, 6, and 9. And we define B as a set of 2, 4, 6, and 8. Okay, now, and the universal set are all the numbers from 0 to 10. Okay, all of the integers from 0 to 10. Okay, so now, find the intersection of the complement of A and B. So in other words, let's think about this. So we want all of the elements that are not in A and in B. Okay? So we want all of the elements that are not in A and in B. Okay, so what's not in A? Well, A is 3, 6, 9, which means everything that's not in A is going to be 0, 1, 2, 4, 5, 7, 8, and 10. Okay, now which one of those 8 numbers that I just listed are in B? Okay, so what numbers are not in A, but they are in B? Well, 2's not in A, and 2's in B. 4 is not in A, and 4 is in B. Well, 6 is in A and B, so that won't work. We want things that are not in A and in B. 9, what else? Oh, 8. 8 is not in A, but in B. So we've got 3 elements that make up this set, right? Because this is a set. Okay, so what are the numbers? Well, it's going to be 2, 4, and 8. So the intersection of not A, or the complement of A, and B is going to be 2, 4, and 8. And so notice how, again, this is the way I would do it until you're comfortable with it. Write out the complement of A. So the complement of A is the set of 0, 1, 2, 4, 5, 7, 8, and 10. B is, again, 2, 4, 6, 8. And so the intersection of these two are what's in both, right? Not A and B. Okay, so in that case, we get 2, 4, and 8. So where do they overlap? They overlap at 2, 4, and 8. So we have the set of 2, 4, and 8. Now, in this Venn diagram, we call this disjoint sets, or mutually exclusive. Okay, so we're going to talk about this later, but I'll use that term interchangeably as well. So we call these disjoint sets or mutually exclusive sets. So they're disjoint because there is no overlap. They're mutually exclusive, right? They exclude each other from each other's sets. No overlap. If there's no overlap, that means that they don't have anything in common. Okay, so this is the way we visualize it in the universe. Okay, now one of the properties of disjoint sets is for any two sets, if they are disjoint, right, then the intersection is empty, right? There's no intersection. They don't have anything in common. So the intersection of A and B, if they are disjoint sets, is the empty set, which means because the intersection is empty. So we get the empty set. So A intersect B is empty, is the empty set if they're disjoint. Now the union of two sets. The union of two sets is where we're going to pool all of the sets together, all of the elements together, and we get rid of duplicates. Okay? So basically, if we want to take the union of two sets, we're going to put them both together. We're going to make a union of them, right? So the union of two sets A and B is where we're going to basically take everything in A and everything in B, put them all together, and get rid of any duplicates. Okay? And so we use the U, this U symbol here, as a union. So A union B is we're going to say all of the elements in A, we want the set of all elements such that the X is an element of A, or, there's another keyword, or X is an element of B, or both. So we're going to say, hey, to get the union, we want all of the elements that are in A, or the elements of B, or both. So if it's an element of A, or if it's an element of B, or both, then it's in the union. Okay, so that means everything that's shaded blue is the union of A and B. Okay, so now let's go back to our sets here. So now we have 4 sets, right? So we have set A, B, C, and then our universe, right? Our universal set. So A is defined as follows, right? These numbers, as a set of these numbers. B is defined as a set of these numbers. C is the set of these numbers. And of course, the universe is the set of the integers from 0 to 12, okay? So now this is what we want to find. Ooh, this is a good one. Okay, so let's take this piece by piece. Okay, so we want A union the set of B intersect complement of C. Okay, so now let's take this piece first. Okay, let's take the intersection. So we want not C. Well, not C is everything that's not in C, but in the universe. So what's not in C, but in the universe? Well, 6, 7, 8, 9, 10, 11, 12, and 0. Okay, so in this case here, we end up with 8, right? So we're going to have 0, and then 6, 7, 8, 9, 10, 11, 12. Okay. Now, B is this. So what elements are in B and not in C? Well, 6, 9, and 12. So 6, 9, and 12 are in B, but not in C. So that means that they're going to be in this intersection. Okay, so now that we've got that set, now we've got a set of 3, which is 6, 9, and 12. Now we want the union of A and this set. So that means we're going to take everything in A and everything in here, put them all together, and if there are any duplicates, we just get rid of the duplicates. Okay, so that there's only one of each. So what we're going to do is we're going to take 1, 3, 5, 7, 9, and 11, and we're going to add it to this set, which we've found is 6, 9, and 12. Okay, now 6 is not in here, but 9 is, so we're going to get rid of one of the 9s. Okay, and then we've got, that's the only duplicate that we have. So our final answer is going to be the set of 1, 3, 5, 6, 7, 9, 11, and 12. Okay, and so here's the solution. Okay, so make sure you walk through this. Here's the complement of C. Here's the intersection of the complement of C and B. So here's B, and here's C. And of course, the numbers that are in common is 6, 9, and 12. Okay, and then now we get the union of this set and 6, 9, and 12. Well, we put them all together, right? And we get rid of the duplicate 9. Okay, and we end up with the same answer that I said. Okay, now let's look at this example. So here we have the New York Stock Exchange, and we've got typical high, low, close, and change for the day for all these different companies that are on the New York Stock. So here, what do we want? Oops. So what are we trying to do here? Let's go back. Let's see how many different combinations there are that we could have of different stock. Well, we could have, let's see, we got 1, 2, 3, 4, 5, 6. So in this case here, we're going to end up with 64 different subsets, okay, of having these different stocks, okay. But let's get out of here for a second. Hold on, because I want to go to Pearson here, and I want to, where is it? Okay, so if we go here, it says for the following table of 52-week low high prices, the closing price and the change from the previous day for 6 stocks on the Standard & Poor's New York Stock Exchange is listed below. And so now what they want to do is they're asking us some questions here. Okay, so here it says, oh, come on now, where's it at? It says, let the universal set U consist of 6 stocks listed in the table. Okay, let A contain all the stocks with a high price greater than 80. B is all the stocks with a closing price between 40 and 105. And let the set C be all the stocks with a positive price change. And D is all the stocks with a low price less than 40. Okay, so again, write this all down, okay? Because you're going to want to keep track of this so that you can get the correct answer. Now, so it says we want the complement of A. Okay, well, what's A? A contains all stocks with a high price greater than 80. Okay, well, that means the complement would be all of the stocks that have a high price of less than or equal to 80. Okay, so which ones have a price of less than or equal to 80? Well, if we go back here, which ones have a high price of less than or equal to 80? Well, the only ones that have a price of less than or equal to 80 would be these two, AT&T and Coca-Cola, which is what they had. Okay, right here. Okay, now, what about the intersection between A and C? Well, A is the highs are greater than 80. C is all stocks with positive price change. Okay, so let's go back and say, okay, well, which ones have both of those? So we want higher than 80. So that's these 4. Oops, excuse me, these 4 for the high, these 4. And then with positive price change. So which ones have both higher than 80 high and a positive price change? Well, the only 3 that have both would be McDonald's, Pepsi-Cola, and Walt Disney. And let's see what they got. McDonald's, PepsiCo, and Walt Disney. All right, good. So now, what about C? B union D. So B is all stocks with closing prices between 40 and 105. And D is low prices with a low price of less than $40. So we want closing price between 40 and 100 or low price of less than 40. So now this is a union, so it's going to be one or the other or both. Okay, so we're looking at closing prices and low prices. So we want closing prices between what? 40 and 104, right? If I remember, or 105, 40 and 105. So closing price and low price. So closing price between 40 and 105. Okay, so we've got these two and these three. So we got these three. So the only one that doesn't fit is Costco. So we've got these three, or has a low of less than $40, which would be these two. So if we pool all of these together, well, we get the same five. We get AT&T, Coca-Cola, McDonald's, PepsiCo, and Walt Disney. So the only one we don't get is Costco. Let's see if that's what we got. Oh, where is it at? Right here. So, and there we go. Right? The only one that didn't make it in was Costco. Okay. So, other than that, I think that's it. So if you have any questions, again, make sure there are plenty of examples in the textbook. Do the your turns. Okay. Do the other examples. Make sure you understand how sets work, how they relate to each other, subsets, complements, the whole thing. Okay. Do the practice problems. Do the exercise at the end of the chapter. Okay, or at the end of the section rather. Okay. The more you practice, the better. Make sure you write down your questions. If you get stuck in anything, write it down or email me. Bring it to class. We'll work out in class. Okay. Other than that, have a great day, and I'll talk to you later. Bye-bye.